This is an e-learning video from Anasazi Instruments. Today's topic is interpretation of NMR spectra for proton. There are several important aspects when you're interpreting proton spectra. These include how many peaks are in the spectrum and their chemical shifts, how the different resonances integrate so we can get a ratio of one resonance to the others, and the splitting patterns that give us information about adjacent protons. So what affects the chemical shift? The electronic environment within the molecule determines the chemical shift. Besides the field of the magnet that you put the sample in, the total magnetic field experienced by the proton, by the individual protons, is dependent upon the currents of electrons in the molecular orbitals. So when you have higher electron density around some protons, that's going to lead to lower NMR frequencies. We'll see that in a little while. Similarly, the electron distribution for different protons is going to be different depending on local geometry, including what partners the protons are bound to: oxygen, carbon, nitrogen, and so on. Another thing that affects it is nearby double bonds and electronegative atoms that pull electron density away from other atoms. Similarly, bond distances and bond angles are also going to affect the chemical shift. The magnitude of a chemical shift is always given with respect to a reference compound. The most common method for referencing the chemical shift is internal referencing. Internal referencing means that it's looking at something in the NMR tube along with your sample. Sometimes a solvent peak is used, but not all compounds can be dissolved in every solvent. So usually a non-interacting substance is added directly to the NMR tube. For most work in the area of organic chemistry, the use of tetramethylsilane is used, and we abbreviate that as TMS. The chemical shift of TMS is set to 0 ppm for both proton and carbon spectroscopy. So when we look at the spectrum at the bottom of the screen, the peak at 1.2 ppm is referenced compared to TMS at 0. Similarly, the peak at 2.7 ppm is referenced compared to TMS at 0. So we always have to have a chemical shift reference whenever we're talking about chemical shifts. So let's talk a little bit about the scale of chemical shifts. The chemical shift is magnetic field independent. That is, the chemical shift is going to be the same on a 90 megahertz spectrometer as it is on a 400 megahertz spectrometer. This allows comparison of signals recorded on different systems. So I can look at a sample on my 90 megahertz, and a colleague can look at a similar sample on a 400, and the ppm scale means the same thing. The chemical shift is reported in units of parts per million, which is a dimensionless scale that describes the energy level of a signal relative to a reference. As we mentioned, TMS equals 0. Proton NMR spectra generally fall in the range of 0 to 14 ppm. When you're calculating a chemical shift, we calculate the difference between the frequency of the sample and the frequency of the reference in regards to the frequency of the spectrometer. So let's do an example here. Let's say we have an NMR signal that shows up at 240 Hertz from the TMS reference peak on a spectrometer operating at 60 megahertz. What is the chemical shift of this resonance? So we have 240 Hertz is our sample frequency. 0 Hertz is our reference for TMS. The spectrometer frequency is 60 megahertz, or 60 times 10 to the 6 Hertz. This gives 4 divided by 1 million, which is 4 parts per million. That's where we get the scale from. So over the years, the chemical shifts of many different substituents has been studied exhaustively. And we have a map of where certain chemical shifts show up. Now, if you're looking at a sample and there's a chemical shift out at 11.5 ppm, you can be pretty certain that there's a carboxylic acid in this molecule. If you're looking at something that's around 7 ppm though, you'll notice that there are different substituents that give a chemical shift in that range. Likewise, if we're down below 3 ppm, there's a lot of different groups that show up in that area. While chemical shift is important, it's not the be-all end-all of determining what your sample is. So let's take a look at an example. So using just the chemical shift information, first, how many signals are there? 3. Where are they? Let's look at the ppm scale at the bottom of the axis there. We're at about 1.2 ppm, 3.6 ppm, and 7.2 ppm. If we look over a certain range, consider the peaks at 7.2. These could be benzene ring peak, double bonded carbons, or something with nitrogen. On the right, down at 1.2, we think that might be a methyl group, but it's not certain. So using just the chemical shift, it is difficult to determine the structure. So let's take a look at scalar or J couplings. The scalar or J coupling is a through bond interaction where the spin of one or more nuclei perturb the energy levels of neighboring nuclei and splitting those peaks into multiplets. J coupling is measured in Hertz and is also independent of the magnetic field strength. So a coupling that you measure on a 90 is going to be the same coupling you measure on a 400. The number of peaks that are observed in a multiplet follows the n+1 rule. A peak will be split into n+1 peaks where n is the number of adjacent protons. Adjacent protons mean protons on the carbon next to the peak you're looking at. The splitting pattern and the heights of the individual peaks within the multiplet will depend upon how many ways the spins of each nuclei can occur. So for instance, if your adjacent carbon has 1 proton, the peak is going to be split into 2. The pattern is going to be a 1-to-1 doublet, and there's a picture of a doublet there on the right. Similarly, if you have a CH2 and a neighboring carbon, this is going to split your resonance into 3 peaks. The splitting pattern is going to be a 1-to-2-to-1 ratio, giving a triplet. Further splitting can occur if a resonance has adjacent protons on more than one neighboring carbon atom. So for instance, if you are sandwiched between 2 carbons that both have protons, you can get multiple splittings. So if you have a single proton on one side and on the other, the number of peaks would be 2 times 2, that's n+1 times n+1 equals 4, and your splitting pattern is going to be a doublet of doublets. Let's look at this a little bit further so we can really understand it. Recall that each proton nucleus can be either spin up or spin down. The average number of spin up and spin down configurations is what is observed in the splitting. For instance, let's look at the ethyl alcohol molecule. The methylene has 2 protons, which gives 3 average spin states. Notice that we have 1 spin state where both are spin up, 1 is both spin down, and 2 where the spin states are spin down, spin up, spin down. The methyl peak has 3 protons associated with it, which gives 4 average spin states. Notice there's 1 spin state where they're all spin up, 1 all spin down, and then several where you have 2 up or 2 down. The intensity of each peak in the multiplet is dependent upon these spin states. So you're going to get a 1 to 2 to 1 ratio if you're next to a CH2. You're going to get a 1 to 3 to 3 to 1 ratio if you're next to a CH3. So if we look at the methyl peak is split by the methylene and gives a 1 to 2 to 1 ratio. Similarly, the methylene is next to the methyl, which gives it a quartet with a 1 to 3 to 3 to 1 ratio. These are integrals, not peak heights, so it's a little bit different. The magnitude of the coupling constant is the same for each multiplet. The coupling constant is how wide apart the peaks are. So if we look at the methylene, we see that all those peaks are 7.6 hertz apart. If we look at the methyl, we would expect those to also be 7.6 hertz apart. So that's how we determine nearby neighbors when we're looking at NMR spectra. Let's go back to our example that we looked at earlier. So using now both chemical shift and J coupling information, let's see if we can guess what this is. So here we think we've got some type of benzene ring or double bonded. Down here we see we have a quartet, 4 peaks, and a triplet, 3 peaks. The quartet indicates that there's 3 adjacent protons. The triplet means there's 2 adjacent protons. We measure the coupling. They both measure 7.6 hertz, so we're pretty sure they're next to each other. And we can assume that this is a ethyl group. So we're making some progress as to determining how to interpret this spectrum. Our final step is to look at integration. The integration of an NMR spectrum reveals the number of protons that are associated with each resonance. More accurately, integration gives the ratio of protons for each signal in the entire spectrum. Let's look at some molecules to see how their signals integrate. So here we again have ethyl alcohol. The total number of signals is 3. The spectrum would integrate to 1 to 2 to 3. What about if a molecule has symmetry? Some molecules have a symmetry axis or more, and the presence of a symmetry axis will give a lower number of signals that integrate to larger values. Let's look at some molecules with symmetry and see how their signals integrate. So this is 2-methylprop-1-ene. So the number of signals, we're not quite sure yet. We'll take a look at that in a minute. Is there a symmetry axis? Yes. That means that the 2 methyl groups are equivalent. We'll give 1 signal. The protons on the carbon that's double bonded are equivalent. We'll give 1 signal. So we would expect this to integrate 6 to 2. Now notice, from what we know before, that the 2 methyl groups have no adjacent protons, which means they'll show up as a singlet. Similarly, the protons on the double bonded carbon have no adjacent protons, and they'll also show up as a singlet. Another feature in many molecules is a benzene ring. And recall that a benzene molecule has a single peak since all the protons are equivalent. However, when a benzene ring has 1 or more substituents, the chemical shifts, splittings, and integrations will all take on familiar patterns. You will see these patterns repeatedly as you observe more and more spectra. So this is one where we have a single substituted benzene that has just an alkyl group on it. It doesn't really affect the chemical shifts very much, and we get basically a slightly split single peak. If we look at something that has an electronegative substituent, like a carbonyl, that's going to pull electron density away from the nearby protons, deshielding part of the benzene ring, and it actually splits these resonances into multiple peaks. If we look at something that's ortho-substituted with something electron withdrawing, we'll get a different interesting pattern. And finally, if we have something that's para-substituted with alkyl groups, we'll see that we get this familiar doublet that has kind of a Batman look to it. So let's look at some spectra that have some benzene rings in them. Here's one. This is 1,4-dimethylbenzene. Total number of signals, we're not quite sure yet. Let's take a look. Is there a symmetry axis? Yes, actually there's two. So if we look at these two methyl peaks are going to be equivalent. All the protons on the benzene ring are equivalent. So we're going to get integrations of 6 to 4. Notice that the two methyl groups have no adjacent protons, and those will show up as a singlet. And the benzene ring protons each have one adjacent protons and will show up as a doublet like we saw just a minute ago. Let's also look at another molecule that has a benzene ring in it. This is 1-phenylpropane-1-one. The number of signals is going to be 3 or 4. Let's take a look at it. If we look here, there's a double bonded oxygen. That is going to pull electron density away from the nearby protons and cause the benzene ring peaks to split. So we think we're going to get 2 to 3 to 2 to 3 integration ratios. So let's go back and look at the spectrum we've been analyzing throughout the course of this video. Notice now that the integrations are present. We see our 3 signals. We see a quartet and triplet indicating the presence of an ethyl group. Our integrations are 5 to 2 to 3. So we are going to take a guess and assume that this is ethylbenzene. There are other spectra that will look similar to this, and by trial and error, you'll get much better at analyzing spectra as you go along. Here's an example of a spectrum that looks very similar to ethylbenzene. You'll notice that it has the quartet and triplet, as well as a area in the benzene ring region that integrates to 4 instead of 5. So that would be a double substituted benzene ring. Notice that the quartet in the middle is all the way down to 4.3 ppm. The reason those get pulled downfield is when they're next to an atom that pulls electron density away from them, basically de-shielding that nucleus. Let's take a look a little closer at it. So here's the spectrum from the previous page. We'll notice that we have our 3 signals. We have the triplet and quartet, and our integrations of 4 to 4 to 6. In the area of the benzene ring, we're going to assume that it's an ortho-substituted pattern. In the area of the alkyls, we notice that we've got a typical pattern for an ethyl group. However, you'll notice that they do not integrate to 2 to 3. It is double. The reason that this methylene is so much further down than in the ethylbenzene is it's next to a group that is drawing electron density away from that group. So we're going to assume that it's next to an oxygen. So putting this all together, we see that this is a spectrum of diethyl phthalate. You notice that it's ortho-substituted on the benzene ring, and the methylene groups are next to an oxygen, which is going to de-shield them. Similarly, the integrations come out right, 4 for the benzene ring, and we have 2 ethyl groups that are equivalent. This is another example. We notice that there are a total of 5 signals. The triplet, multiplet, triplet in the alkyl region integrates to 2 to 2 to 3, and the benzene ring region has something that integrates to 2 to 3. We know by now that when something integrates to 5, it's a single substituted benzene. You notice it's split into multiple peaks, so there's something that's de-shielding some of the protons. Down in this region, we know that a methylene that's next to an oxygen will be pulled to a higher frequency. Further, we notice that it's split into a triplet, so we know that it's next to a CH2. We look down at the peak that integrates to 3. We assume that's a CH3. Again, it's split into a triplet, so we know that it's next to a CH2. There's a lot of information here. We put this all together and draw out the molecule from what we've learned, and we see that this is propylbenzoate. All the integrations come out right. The methylene next to the oxygen is pulled to higher frequency because it's de-shielded, and the carbonyl attached to the benzene ring is de-shielding some of those protons. So how do we use this information to interpret spectra going forward? We're going to identify the number of peaks that are in a spectrum. The information about their chemical shifts is going to tell us what type of substituents there are, whether they're alkyl groups, benzene, nitrogen. The multiplets that we see are going to help us identify which peaks are next to each other, and the integrations are going to give us the ratios of all the protons in the molecule so that we can come up with a good structure.